Now let's look at an example of how to determine stability of an equilibrium in the discrete case, in a discrete dynamical system. The differences are very small, but we still need to pay attention to some aspect of this computation. Alright, let's look at an example over here. This is actually a very famous example. It's called the quadratic system. So the system over here we have looks like this. It's xt plus 1 is equal to f of xt. So this is a discrete system. And how to find equilibrium now? It's called fixed point. Fixed point, that means if you apply this capital F, it's not going to change. So this is the way to find a fixed point or an equilibrium. After you find x star, how to determine the stability? We still take the derivative, and we find the derivative, and we look at, instead of its sign, we look at whether it's greater than 1 or less than 1, its absolute value. If the absolute value is greater than 1, then this is going to be unstable. If the absolute value at an equilibrium is less than 1, then it's going to be stable. Okay. So let's look at this example over here. In this example, we have a parameter lambda. Lambda is a constant. Okay. So first, let's find x star. That means x star is going to be equal to lambda x star and 1 minus x star. So replace xt and x sub t plus 1 all by x. You cannot say we're going to divide x star both sides. You can factor things out. So you can have x star minus lambda x star and 1 minus x star is equal to 0. And then you can factor x star out. And then you have 1 minus lambda, 1 minus x star. It's going to be equal to 0. So you have 2 again. X star is equal to 0. Let's call this x star 1, x2. Then you have 1 minus lambda, 1 minus x star equal to 0. So 1 minus x star is equal to 1 over lambda, and x star is 1 minus 1 over lambda. Usually our lambda is bigger than 0. So we don't have a 0 denominator over here. Now let's determine the stability of these two equilibria. Take the derivative of your function. Your function is lambda x, 1 minus x. It's a quadratic function, so you can just multiply out and see what we have. Lambda minus x squared. This is what we have. So if you take the derivative, then you can have lambda and minus 2 lambda x. So now we need to look at the derivative's absolute value, and that's lambda 1 minus 2x. Okay. So let's look at the first one. At x star 1 is equal to 0. Okay. And then we have f prime of 0 is equal to lambda, and we have 1 over here. So this is exactly lambda. So we have the following conclusion. If lambda is greater than 1, then 0 is unstable. If lambda is less than 1, then 0 is stable. Now you may ask what's going to happen if lambda is equal to 1. Then this derivative method fails. We can also use other geometric method to look at its stability, but that's not the topic of this segment. So that's it. We want to just look at these two regions for the lambda. Now let's look at the other situation, other point. X star is equal to 1 minus 1 over lambda. So we plug it in, then we have f prime of x is equal to lambda times 1 minus 2, 1 minus 1 over lambda. And that will give us lambda over here, 1 minus 2, and plus 2 over lambda. So we have, let's multiply lambda inside. So we will have negative lambda and plus 2. So that's what we have. Or you can say 2 minus lambda. This is what we have. And so our conclusion is, if 2 minus lambda is bigger than 1, then unstable. Then x2 star unstable. And if 2 minus lambda is less than 1, then x2 star is stable. Now notice over here, 2 minus lambda less than 1 implies lambda is between 1 and 3. So if lambda is between 1 and 3, then we have this one stable. If lambda is not between 1 and 3, then this equilibrium isn't stable.